let's start. So, welcome back, morning and afternoon. And it's a great pleasure for me to introduce Professor Benoit Daniel from University of Lorraine. I don't know how to pronounce Lorraine. Yes, thank you. The title of his talk is On Parallel Mean Curvature Surface in Product Manifolds. So, thank you.
Okay, thank you. Thanks for the organizers for the invitation to give a talk in this conference and for organizing this online meeting. I hope the next one will be a presential one. So the title of my talk is On Parallel Mean Curvature Surfaces in Product Manifolds. And I'm going to talk about a joint work with Yuri Domingos and Feliciano Vittorio. So, as it is said in the title, I am going to be interested here in parallel mean curvature surfaces. So parallel mean curvature surfaces are a certain generalization of constant mean curvature surfaces, but in higher codimension. So the definition is the following. We consider a Riemannian manifold M, dimension n. The parallel mean curvature surface is a surface whose mean curvature vector, H, satisfies this equation. The normal connection of H is identically 0. And in particular, this property implies that the norm of the mean curvature is constant on the surface. Why? Because if you compute the derivative of the norm of H, of this vector H, it will appear this nabla perp H, and so it will give you 0 to do the computation. So the norm is constant. And I will, in this talk, I will exclude the case of minimal surfaces. I will not consider minimal surfaces. I will only consider parallel mean curvature surfaces which are not minimal. And I will use the following notation. For a given constant H is a real number here, positive, I will call HPMC surface a parallel mean curvature surface with mean curvature vector as norm H. And I will call an HPMC immersion an immersion whose image is an HPMC surface. Okay, so this is a generalization of CMC surfaces, but in some, from different aspects, it is quite different. For example, it is very rigid. It is very difficult to find examples. You don't have, for example, the plateau technique. And so there are very few it's not easy to construct examples. And so one of the goals of this talk will be a classification of certain surfaces, but also an interesting point in this classification is that it will produce new examples. So let me first give you some notation and recall a few facts. So I will denote by Mn of C the n-dimensional space form of sectional curvature C. So we have, of course, 3 cases. If C is positive, we have a sphere of constant curvature. If C equals 0, we have Euclidean space, Rn. And if C, there is a misprint, of course, here. The third line is C negative. Mn of C is hyperbolic space, Hn of C. So here there is a misprint. It is negative. And in the sequel, I will use, when I'm talking about the surface, I will denote by K its intrinsic curvature. I mean just the curvature of the metric. So, we are particularly interested in classifying PMC surfaces with constant intrinsic curvature. So this is a very overdetermined problem because it is 2 very strong conditions. So when we ask, given a certain ambient manifold, what are PMC surfaces with constant intrinsic curvature, what we should expect is very few examples. We should expect trivial examples and maybe some exceptional examples. This is the kind of result you can expect because it is too strong. And there is some results known about this in dimension 4, for example. First result is a result by Kenmotsu in this is about minimal surfaces. So in 4-dimensional space form, minimal surfaces with constant intrinsic curvature are either totally geodesic with k equals c, or part of a Clifford torus with k equals 0, geodesic S3, or part of Veronese surface. Also, we have a result by Hoffman for the case of PMC surfaces with constant intrinsic curvature, and also there is a classification with very few examples. First, we have either k equals 0 or k equals h2 plus c, so only two possible values for the intrinsic curvature. And we have a classification in each case. If c is non-negative, then the surface is either a part of a product of circles with k equals 0 or a part of a true sphere with k equals h2 plus c, where h denotes the norm of the mean curvature. And also, when we have classification due to Hirakawa in complex space forms. So complex space forms are in dimension 4, you have C2, which is just R4, H2 of it is a hyperbolic complex plane, and we have CP2, which is the complex projective plane with holomorphic curvature C here. Also C2, C negative for CH2. And there is also a classification. And in this case, we have either product of circles or a cylinder or a round sphere. And there are also two exceptions. One of them is called a slant surface, and another one was a new example found by Hirakawa, which was found by doing a kind of separation of variables. It is an example that can be explicited in terms of solutions to an ODE. So roughly speaking, in these classifications, we see that we have some kind of trivial examples and some exceptional examples. Okay. So now the goal of this talk will be to provide a classification result like this when the ambient manifold is M2 of C cross M2 of C. For C different from 0, otherwise it is just R4. So it means just S2 cross S2 or H2 cross H2, because up to scaling, I will assume that C is +1 or -1, it's just a normalization. And these manifolds are quite interesting because there are some homogeneous manifolds. So when to expect some classification result like this, it's a natural hypothesis to assume that the manifold is homogeneous. Otherwise, it's not really. We cannot really expect to have such a nice classification result because it would depend on the point. And in a homogeneous manifold, we will be interested, of course, of classification results up to congruencies. I mean, up to isometries of the ambient manifold. So this is one of the motivation, how to extend these results in some other homogeneous manifolds. And among them, this one has the property of being Kähler-Einstein. And we will see that, I mean, not really direct consequence from this, but also there is a result from Torralbo and Urbano, which I will explain, which relates this problem of finding TMC surfaces in M2 of C cross M2 of C with a problem of studying CMC surfaces in M2 cross R. I will explain this next. And this is very important in this argument, in this Torralbo-Urbano classification, to have the same value of C in the two factors. It doesn't work otherwise. Okay. So first question is, can we find just examples? of PMC surfaces in these manifolds. Just examples, not even with constant intrinsic curvature, but just finding examples. An important observation is that the product manifold S2 cross R is isometrically immersed into S2 cross S2 as a totally geodesic, S2 cross S1. What do I mean? Here, S1, I take S1 as a geodesic of S2, and I make the product S2 cross S1 in S2 cross S2, and this is totally geodesic, and this is isometric to a quotient of S2 cross R, like S2 times R divided by 2 pi Z, for example. So as an immersion, we can think as S2 cross R as a totally geodesic immersed surface of S2 cross S2. And this is the same in H2 cross H2. If I take R, a geodesic, in the second factor H2, then I get a copy of H2 cross R, which is totally geodesic. So this will be very important for us. We will think in the sequel as H2 cross R as a totally geodesic submanifold of H2 cross H2, and also S2 cross R as a totally geodesic immersed submanifold of S2 cross S2. So why is it important? Because it provides examples. Actually, since M2 cross R is totally geodesic, if I take a CMC surface in this M2 cross R, this will give me a PMC surface in M2 cross M2. So, in some sense, it gives us examples of PMC surfaces, but they can be reduced to CMC surfaces in three-dimensional totally geodesic manifold. So it's not really new examples of PMC surfaces. It's a kind of degenerate case. Another example indicated by Torralbo and Urbano is the product of constant curvature curves. We can compute this. If I take gamma 1 and gamma 2, some curves in M2, with constant curvature K1 and K2, not both 0, then if I take just the product, it gives me an HPMC surface with the mean curvature, the norm of the mean curvature vector given by this formula, 4H2 equals K1 square plus K2 square. So here, of course, I'm just avoiding the minimal case, which occurs in the same way, where K1 and K2 are 0. So this is the only reason why I'm excluding this case. So I will not consider minimal surfaces. And there is also another example found by Torralbo and Urbano in H2 cross H2. So I will call this the Torralbo-Urbano surface. For any value h between 0 and 1/2, they introduce an explicit isometric embedding of the hyperbolic plane of curvature k equals 4H2 minus 1 that does not lie in a totally geodesic H2 cross R. Okay. Yes, I forgot to say that the example number 2 here is flat. So the Torralbo-Urbano surface is another type of example. So this example, and again, this example, you can find the formula, but it's not really useful for me to give you the formula, but you can also, this example is obtained by separation of variable, and it's expressed in terms of solutions to some ODEs. So it is some kind of explicit example. And they found this example when they were looking for some PMC surfaces satisfying some properties. And actually in their paper, they also provide some other examples of PMC surfaces, which are, but not with constant intrinsic curvature. So they provide some other examples, generalizing this Torralbo-Urbano surface here. But it's not easy to find examples. Actually, they provide some examples, and there are not many known examples, apart from the ones in the paper of Torralbo and Urbano. Okay. So here, these three examples, these three classes of examples, they also have this additional property that the mean curvature, the intrinsic curvature is constant, sorry. So now let me give some preliminaries about the correspondence between PMC surfaces and CMC surfaces. So I will fix a conformal structure J on M2 of C. I mean, by this, I just mean rotation of angle pi over 2. And I will let omega be the corresponding Keller form. And we have these forms I call pi j the projections. And we consider these forms omega 1, which is pi 1 star omega plus pi 2 star omega, and omega 2, which is pi 1 star omega minus pi 2 star omega. And I consider a positive number h, and I consider a surface sigma oriented, simply connected with a Riemannian metric ds squared. And phi will be a PMC, an HPMC isometric immersion of sigma into M2 cross M2. And this manifold M2 cross M2 has two Keller structures, J1, which is just the pair JJ, and J2, which is the pair J minus J. And associated to these two Keller structures, we can consider what we call the Keller functions, nu J, defined by this formula here. Phi star omega J is nu J omega of sigma, where omega of sigma is just the area form. Okay. I'm not going to enter more into details because it's not really necessary for what I'm going to explain next. But we have to remember that when I have a PMC isometric immersions, I have these two Keller functions nu1 and nu2, which are associated to the two Keller structures of M2 of C cross M2 of C. And they are important because we have some kind of, we can reduce the problem of finding an isometric immersions to a problem of finding solutions to a set of PDEs. Okay? So if I have an HPMC immersion like this, I can consider the function nu1 and nu2, and also I can consider the quantities which I call dH1 and dH2. So I'm not going to explain what is this, but roughly speaking, it is something related to moving frames. No? When we look at immersions like this, we look like there is a classical technique of moving frames, looking at Frenet type equations. Okay, and these dH1, dH2, they appear when we compute the derivatives of phi, and we express these derivatives in a certain moving frames. And some of the coordinates appearing in these moving frames, equations, some of these coordinates are related to the quantities here, which I call dH1 and dH2. So you have to think of dH1 and dH2 as things related to the derivatives of phi. Okay. Actually, in the paper of Toralbo and Obano, it's not written like this. It's written in another way, but this way here is equivalent, and it will be more convenient for what I'm going to explain. So here I'm saying two things. If I have an HPMC immersion, I have these quantities. So of course I have the metric ds squared, which is fixed, and I have these quantities nu1 dH1, nu2 dH2, and we can show that the Gauss-Codazzi and other compatibility equations show that there are solutions of this set of four equations like this. So we have two PDEs of order 1 and we have two PDEs of order 2. Okay? And there is a converse also in the paper of Toralbo and Ubano. If I have a metric ds squared and if I have some solutions of nu1 dH1, nu2 dH2 of this system, then it gives me an HPMC immersion. So there is a correspondence between HPMC isometric immersions and solutions, four tuples, nu1 dH1, nu2 dH2, solutions to this. Okay. But this actually, this set of solution is also related to CMC isometric immersions. Because if I just take one pair Here I have two pairs actually. I have nu1 dH1 and nu2 dH2. It is two pairs of solutions to this. But if I just take one pair of solution, nu1 dH1 for example, then it turns out that this set of equations is a set of compatibility equations for a CMC isometric immersions. It means that if I take a CMC isometric immersions into M2 cross R, then I can define nu and H satisfying solutions satisfying this system, and conversely, if I have nu and H solution to this system, then I get an isometric immersion, which is CMC in M2 cross R. Okay? So nu1 H1 gives me a CMC isometric immersion. Nu2 H2 gives me also a CMC isometric immersion. So when I have an HPMC immersion, isometric immersion here, I forgot isometric here, an HPMC isometric immersion gives me two HCMC isometric immersions, and conversely, two HCMC isometric immersions into M2 cross R gives me one HPMC isometric immersion into M2 cross M2. Okay, this is what I'm saying here. Also, there is something which I'm not going to explain very in detail. All this is, of course, modulo isometries in the connected component of the identity. It means we can apply direct isometries in each factor. But we can get also the other isometries by some standard transformation, for example, permutation of the indices or multiplying some quantities by -1. And in this way, we will get also the isometries which are not in the isometric, in the identity, in the connected component of the identity. Okay, so this is the correspondence. One CMC. So Graham's question. Sorry, where can I see it again? Are the CMC immersions independent? Yes, they are independent. I mean, the only relation is that they induce the same metric. The metric is fixed, and I consider two CMC immersions of the surface with this given metric, and they are not related one to each other. They are CMC isometric immersions, exactly. Yes. Actually, this is, yes, but this is not easy to find non-trivial examples of this, actually. If you think of this in R3, if I have two CMC isometric immersions of the same surface into R3 with the same value of the mean curvature, then it's known that they are associate. They are associate surface in the sense that they are obtained by rotating the traceless part of the shape operator. For example, it's like a nodoid and unduloid or things like that. We have a one parameter family of CMC isometric immersions, all obtained by rotating the traceless part of the second fundamental form. And it's the only way to obtain such pair of isometric immersions, non-trivial. But in M2 cross R, it's not, we don't have this. And actually, it is very difficult to find some non-trivial examples of CMC isometric pairs of CMC isometric immersions. This is, in general, it is a very open problem. We don't know whether it exists or not in general, and we don't know if we can find conditions so that it does not exist. But we will see examples in the sequel. Yes, they both have the same mean curvature. H is fixed. Yes, I forgot to say here. I fix the value of H. So H will be the value of the CMC isometric immersions, and it will also be the norm of the mean curvature vector of the PMC isometric immersion. So it's fixed. And also the value of K will be fixed later. Okay. So this is what I was explaining. Yeah? A pair of Tmc isometric immersions into S2 cross R or H2 cross R yields an, okay, here I put the value, the absolute value, because I can consider H negative, it's not really important. So it yields an absolute value of HPMC isometric immersions into S2 cross S2 or H2 cross S2, and conversely, and this is up to congruencies. And also there is an important property, also in the paper by Torralbo and Urbano, is that when, I forgot to say here, phi1 and phi2, yes, I forgot to introduce the notation. Phi1 and phi2 are the CMC immersions, and phi is the PMC immersion. So there is a misprint. Okay, let me correct it. We can do it quickly. Okay, now it should appear corrected. So, important property is that if the two CMC immersions here, if the two CMC immersions are congruent, in other words, if the pair is trivial, then the PMC surface is also trivial. It means that the PMC surface is actually a CMC surface in a totally geodesic S2 cross S1 or H2 cross R. This is what I call trivial PMC immersion. It means the CMC immersions into a three-dimensional, totally geodesic submanifold. Okay, so we have this characterization. In other words, the pair of CMC immersion is trivial if and only if the PMC surface is also trivial. So it's interesting to find non-trivial examples. So you see from this point of view, it is equivalent to find a non-trivial pair of CMC isometric immersions into S2 cross R or H2 cross R, or finding a non-trivial PMC surface in M2 cross M2. Okay, so before of classifying PMC surfaces with constant intrinsic curvature, we will try to classify CMC surfaces with constant intrinsic curvature in M2 cross R. Sorry, N here is 2. It's a misprint. And this is the first result here, which I'm not going to explain in details. But we have the classification. So I consider H different from 0, and sigma, an HCMC surface in M2 cross R with constant intrinsic curvature K. Then we have only 3 examples. First case is K equals 0, and sigma is part of a vertical cylinder. So what is this? It's just, I take the product of the geodesic curve of curvature 2H in a horizontal M2, and the product with the vertical factor R. And the second and third possibilities occur only when C is negative. Then we have K, which is 4H2 plus C, which also has to be negative. And there are 2 possibilities. Sigma is part of an Abresch-Rosenberg lattice surface or a certain helicoidal surface. So briefly, what is an Abresch-Rosenberg lattice surface? You can think of this as a kind of slant plane. I mean the following. So I am in H2 cross R. And if I intersect my surface with a horizontal plane, I will get a hollow cycle. And if I cut this R ARL surface by a vertical plane orthogonal to the horocycles, I will get a geodesic. I will get a slant geodesic in a vertical plane, a slant geodesic of H2 plus R in some vertical plane. So in some sense, this average Rosenberg-Leakey surface is a kind of slant plane. It interpolates horizontal planes and holocylinders. And these surfaces were discovered by Average and Rosenberg when they were classifying CMC surfaces with vanishing Average-Rosenberg differential, and later proved that they had constant intrinsic curvature. So this was a known example. And there is a new example, which I'm not going to describe, but we can compute it. It is a helicoidal surface. So it is a surface which is invariant by one parameter family of screw motions. And the generatrix curve can be expressed in terms of a solution of an ODE. It's not embedded. So we have this classification, and a few ideas to get this classification is a study of the system of equations here. Remember that to a surface I can associate this function nu and h. So nu is called, for those who are familiar to this, nu is called the angle function and h is a height function. So the problem is to study a solution to this in the case where k is constant. And so it's not an obvious study, but it's doable. And we see that only these examples can occur. So vertical cylinders, average Rosenberg-Leakey surface, and new surface of helicoidal type. Okay. So in particular, this gives you non-trivial pairs of CMC isometric emotions. If I take an average Rosenberg-Leakey surface and a helicoidal surface, it gives me two isometric emotions of the hyperbolic plane of constant curvature k with the same incurvature h. Okay? And they are not congruent. The IRL surface and this helicoidal surface are not congruent. So this IRL surface together with the helicoidal surface gives me a non-trivial pair of CMC isometric emotions with h fixed and of the hyperbolic plane of constant curvature k fixed whenever this inequality here is satisfied. So this gives me a non-trivial example of a pair of CMC isometric emotions. Okay. So this is the first step. Now the second step is, well, we have to put this in the Torralbo-Urbano correspondence. The Torralbo-Urbano correspondence takes me that if I want to have a PMC surface with a constant curvature k, I have to take two CMC surfaces with mean curvature of constant curvature k and the same value of h. Okay. So this looks easy, but there is something which we have to take to be careful, is the fact that here this is about surfaces. This is a classification of surfaces, I mean of the images of emotions. But the theorem, the classification of Torralbo and Urbano is about emotions, not about surfaces. So this is what I'm saying here. The previous theorem is about surfaces, but the Torralbo-Urbano correspondence is about emotions. It means that if I take a surface, I can have several parametrization of my surfaces. Or I can reparameterize my surface by an intrinsic isometry. And from the Torralbo-Urbano correspondence point of view, it is a different emotion. So we have to take care, to be careful about this. So what is the idea? Let me state the results. So in S2 SU, it's not very interesting. We only have trivial examples. Okay, we have only k equals 0, and sigma is part of a product of two curves of constant curvatures. Okay, we only have these examples. But when we are in H2 plus H2, we have plenty of new examples. So we have first case, which is k equals 0 and sigma is part of a product of curves of constant curvature, so like in S2 plus S2. But we have all these exceptional surfaces. So the second case is when the relation k equals 4h2 minus 1 and this negative is satisfied, and we have all these classifications. So here I'm writing sigma is part of, but if you assume sigma complete, you can remove the is part of. Because you can have the local, you can even have the local result. But if you assume sigma is complete, you have the classification. So we have, first example, we have the ARL surface in some totally geodesic H2 cross R. We also have the constant intrinsic curvature helicoidal surface that appeared in the previous theorem in some totally geodesic H2 cross R. You also have the Toralbo-Urbano surface, which I mentioned in a previous slide. And we have all these new surfaces. So I'm going to explain this notation in the next slides. So A id of omega is one surface, A zeta of omega is one surface, B eta of omega is one surface, BMS of omega is a one parameter family of surface, and B eta soc ms of omega is also a one parameter family of surfaces. And these are new surfaces, and also they are not pairwise congruent. So it is really different surfaces. Okay, so what is the proof of this? The ideas, at least. So let me introduce some notations. So I'm interested in isometric immersions of the hyperbolic plane of constant curvature k negative, and I assume my numbers k and h are related by this relation. So I consider the half plane model, and I consider z a complex coordinate, and the metric will be given by this formula. So this is a standard half plane model with curvature k. I give an orientation to omega, and I consider the isometry group of omega, which is PSL2R union PSL2 minus R. So the first one is for the direct isometries, the orientation preserving isometries, which are acting like this by homography. And also PSL2 minus of R will give you the indirect isometries. So there are the matrices with determinant -1 here, quotiented by plus or minus the identity, and acting like this. So it's a nice way to express the isometries of the hyperbolic plane. And for some reason that I will explain later, I need to consider these particular matrices. D is a set of diagonal ones like this. T is some upper triangular matrices like this. And I consider these particular matrices here, xi, eta, and zeta. In particular, eta here is an indirect isometry. It's a reflection. Okay. And now, if I consider an isometric, if I consider an immersion, maybe not isometric immersion phi, either into H2 plus R or in H2 plus H2, I will consider the group, the subgroup G phi, which is a group of the isometries of omega, the hyperbolic plane, such that up to congruencies, the immersion phi coincides with the immersion phi composed with F. So in other words, F, this group G phi, is a group of intrinsic isometries of omega that are induced by extrinsic isometries. So if I consider just an easy example, if I consider horizontal H2, if I consider H2 cross constant, H2 cross 0 in H2 plus H2, in H2 plus R, sorry, then all isometries, then all intrinsic isometries come from ambient isometries. But if I consider the Abresch-Rosenberg-Leyti example, which is this kind of slant plane, it's not the case. Here, the group of isometries the group of intrinsic isometries at dimension 3 is the group of isometries of H2. It has dimension 3. But not all of them come from ambient isometries. Actually, only a 2-parameter family come from ambient isometries, but not all of them. For this Abresch-Rosenberg-Leyti surface, there are some intrinsic isometries that do not come from congruencies, from extrinsic isometries. So this is why this group G phi is important. And we can compute them. So we note by X a certain expression for the immersion of the ARL surface, and Y will be an immersion that gives me the helicoidal example. And they can be explicit. I'm not going to write the formula, but we can give explicit formulas from this. And actually, we can compute these groups Gx and Gy. So Gx, you see that it is a 2-dimensional group, and this is exactly what I was explaining. It means that I have a 2-dimensional group of intrinsic isometries coming from extrinsic isometries. And Gy is only 1-dimensional. I only have a 1-dimensional group of isometries coming from extrinsic isometries. And you see that in each case, we have 2 connected components. The first one, which are direct isometries, and the second one, which are indirect isometries. Okay. So now what is the sketch of the proof? So to get my Tmc isometric immersions, yeah, I forget to say that I will explain the proof only in this exceptional case, which is the most difficult one, actually. I will just explain the proof in the case where k is 4H2 minus 1 negative in H2 plus H2. So how can I obtain a PMC isometric immersion? I have to take a pair of CMC isometric immersions. So I have 3 possibilities. I can take 2 copies of X, 1 copy of Y, 1 copy of X, and 2 copies of Y. But remember that you can compose, since I am considering immersions and not surfaces, I can compose by, I can reparameterize my surfaces. It means I can compose by F, where F is an isometric, is an intrinsic isometry. F belongs to the isometry group of omega. Okay? Actually, I could do the same for the first factor on the left here, but it will not give me, because if I reparameterize both the two ones, I just get a reparameterization of the PMC surface. So it is sufficient to consider reparameterization only of the second one. Okay? So I have 3 cases. But if I do this, maybe for a different F, I will still get the same surface. So the problem is, which F give the same PMC surface, which do not give the same PMC surface. So we have to understand whenever 2 isometries F give the same PMC isometric immersions up to congruencies and isometric reparameterization. And this gives me an equivalence relation on the isometry group of omega. Okay? And to illustrate this, I will explain case number 3. Case number 3 is when I take 2 copies of the helicoidal examples, Y and Y composed with F. And in this case, it's not hard to see that 2 isometries F1 and F2 will give me the same PMC immersions up to congruencies if and only if they satisfy this relation F2 equals G1, F1, G2, where G1 and G2 belongs to the group GY, which are the the group of diagonal matrices that appeared in the previous slides. Okay, so it's a kind of double quotient. We have a quotient of PSL2R on the left and on the right by this group GY. This is a kind of strange equivalence relation, but it's a linear algebra exercise to see that we can describe the equivalence classes of this relation. But before doing this, we can think of the dimensions. The isometric group of omega is dimension 3. And I'm doing a quotient on the left and on the right by the group GY, which has dimension 1. So it is natural to expect a space parameterized by one real parameter. Because I have dimension 3, and I make two quotients by something of dimension 1. I expect to have something of dimension 1. And we can show that I can choose. So I have several classes of equivalence. And if I consider only the direct ones, I have the class of the identity. And I have the class of MS, where MS is this matrix. And I can choose S between 0 and I can choose S non-negative here. And also I have some classes corresponding to the indirect ones, which is a class of eta, which appeared in the previous slides, and the composition of eta with this matrix M of S. So this looks quite strange because we are considering some isometries of omega, but this does not seem to have some geometric property. All this seems algebraic. I have no idea whether this has a geometric interpretation. In particular, it doesn't seem to have anything to do with the fact whether the isometry is a parabolic, elliptic, or hyperbolic, or something like that. It's not really clear. So it's a little bit mysterious, but we can do this. And so I have solved my isometric classes. And so to each my equivalent classes, and to each equivalence classes, here I will get a new PMC isometric immersions. Okay. So if I come back to my classification here, so you see that the case where I take twice the helicoidal example gives me the last two ones, BMS of omega and B eta of MS of omega, here, which are two one-parameter families. I have also B eta of omega, and if I take the identity, I just get the second one, which is just a trivial example, which is the helicoidal surface in a totally geodesic H2 gross R. Okay? So the Toralbo-Urbano surface will be obtained if I take twice the ARL surface. And this surface's A identity and A zeta will be obtained if I choose for one of them the ARL surface and for the other one the helicoidal surface. So this corresponds to the three cases I described. Okay. Yes, and maybe just a last remark to conclude. So in particular, in this classification, the five last ones are new. And maybe it's not possible to compute them, even by doing a separation of variables, at least for some of them. Because they don't have, at least for some of them, the last two ones, for example, they don't have some group of intrinsic isometries. So maybe we cannot compute them. We know they exist, but we cannot compute them. Is that it provides some surfaces with extrinsic normal curvature, which is given by this formula here, that does not vanish. And again, this was a, I mean, it was given as a problem whether it exists or not. And so this provides some examples of these surfaces with this property. Okay. And I think I will stop here, and so thanks for your attention.
Thank you very much, Benoit. So, any questions? So, how about the case, this one, with curvature different, the product space?
Well, good question. I think the problem is that in this case, you don't have the Toralbo-Urbano correspondence. Because this Toralbo-Urbano correspondence is very specific to the fact that you have the two, you can exchange the products, and it gives you a very symmetric set of equations. So if you assume different curvatures, it's not really obvious how you can generalize the Toralbo-Urbano argument, because the equations lose a lot of symmetries, and you don't know really what to do. So it's really an open problem. I think so.
So, do you use some structures of product space to transform the normal vector of the surface? Since your mean curvature is not zero, so
yes,
you have a parallel normal vector field, right?
Exactly. Yes.
So what's the difference with the examples of this one?
When
you have 5 new examples. You have 5 new examples, right? You have 5 types of new examples of
yes.
HPMC. So can you say there's some difference of the vector normal vector? I mean the behavior of normal vector.
It's very hard to say because
in the complex case, people use a lot of the normal vector field to construct a base.
Yes.
But in your case, you also use this.
I mean, this construction is in the Toralbo-Urbano argument. They use a moving frame obtained by considering the mean curvature vector, and they rotated in. They also rotated in the normal bundle, and they make a linear combination of both, and they use this as a moving frame. And the quantities that appear, these quantities nu I, hi, that appears, they are related to this moving frame. And then they have a set of equations. And conversely, when they have a solution to this set of equations, they are able to integrate the Frenet equations. But this, if you have C1 different from C2, it will not work. You have to come to these equations, but it will not work. I mean, not easily, like this. The equations are a little bit complicated, so it's not obvious. You have to. You really have to enter into the details of these computations to understand the stuff.
Okay. Thank you very much. Any more questions? So if not, let's thank the speaker again.
Thank you.